Diffusion models are one of the most powerful generative models we have today, and the core idea is surprisingly simple. We start with the real image. In the forward process, we gradually add Gaussian noise to this image over many steps until it becomes pure noise. This process is fixed and does not require learning. The learning happens in the reverse process. Here, the model is trained to iteratively remove noise step by step, starting from random noise and moving back towards a clean image. At each step, the model answers a very specific question. Which part of this signal is noise and which part belongs to the image distribution? Importantly, the model does not need to directly generate pixels from scratch. Instead, it learns to predict the noise added at each step. This turns image generation into a denoising problem, which is much easier to optimize. This idea is closely related to denoising autoencoders but extended into a multi-step stochastic process. However, this approach comes with a major challenge. Images are extremely high dimensional. Most pixel level details like textures or fine noise are not directly related to semantic structures such as objects, shapes or layout. Yet, a diffusion model operating in pixel space must compute gradients across every pixel at every step, making training and sampling very expensive. This leads to a key insight. Separate perceptual detail from semantic structure. Modern diffusion models do this by operating in a latent space instead of pixel space. First, an autoencoder or variational autoencoder compresses the image into a lower dimensional latent representation. This step handles perceptual compression. Then, the diffusion process runs entirely in this latent space where semantic structure is preserved but irrelevant pixel level redundancy is removed. This is exactly the idea behind stable diffusion. Noise is added and removed in the latent space, not the original image space, drastically reducing the computation while preserving visual quality. For the denoising network, the most commonly used architecture is the UNet. Its encoder-decoder structure captures local spatial information while skip connections preserve the fine details across scales, which is crucial for denoising. Finally, diffusion models become truly powerful when we condition them. Conditioning allows us to guide the denoising process using external information such as text, images or other embeddings. This is typically done using cross-attention. The latent image representation provides the queries while the conditioning signal such as text embeddings provide keys and values. As a result, each denoising step is guided toward samples consistent with the conditioning input.